Hey, welcome. Take a moment and settle in. Curiosity brought you here, and if you follow it, it tends to take you further than you expect. Subscribe if you enjoy that journey. Now, let's start at the beginning. You observe a star suspended in the quiet vastness of space. Its core burns with hydrogen, steadily fusing protons into helium, releasing energy that radiates outward in a delicate balance. This process, known as nuclear fusion, supports the star against the inward pull of its own gravity. Over millions of years, layers of fusion build upon one another. Helium fuses into carbon, carbon into oxygen, oxygen into heavier elements, following a sequence determined by temperature and pressure in the core. Each layer functions like a finely tuned engine, sustaining the star's equilibrium while slowly accumulating heavier elements toward the center. You notice that as the star's core evolves, the outer layers remain luminous and steady, masking the intense changes within. Eventually, the star's core becomes dominated by iron, an element that cannot release energy through fusion. Without the ability to generate outward pressure from fusion, the delicate balance collapses. Gravity overwhelms the core, compressing it inward with astonishing intensity. Electrons are forced into protons, forming neutrons through a process called electron capture. In an instant, matter achieves densities that are almost incomprehensible, comparable to the mass of the sun compressed into a sphere only about 20 kilometers across. This transformation marks the birth of a neutron star, a residue of the massive progenitor. The outer layers, unable to resist the sudden loss of pressure support, rebound outward violently. You watch as the star erupts in a supernova, releasing a tremendous amount of energy. Light travels across space, reaching distant observers millions of years later, carrying with it the story of collapse and rebirth. The explosion disperses elements forged in the core into the surrounding interstellar medium, enriching future generations of stars and planets with heavy atoms. Every atom of iron, calcium, or oxygen you encounter on Earth may have originated in one of these cataclysmic events. The supernova is both an ending and a beginning, quietly transforming the cosmos while leaving behind a dense, compact core. You consider the neutron star itself, its structure defined by physics at extreme conditions. Neutrons are packed together so closely that a single teaspoon of this matter would weigh billions of tons. The star's radius is minuscule compared to its mass, creating a surface gravity that bends space and time subtly around it. You sense the influence of general relativity as light and matter curve in response to this concentrated mass. Rotation rates are often rapid at birth, with the neutron star spinning several times per second, though this slows over time as it loses energy. These physical properties distinguish neutron stars from ordinary stars and place them among the most exotic objects in the universe. Within the star, the density increases toward the core. You follow theoretical models suggesting that the interior may host superfluid neutrons and superconducting protons. The arrangement of these particles allows for frictionless flow and extraordinary magnetic behavior. Matter is compressed beyond the atomic scale, forming a lattice of neutrons that can only be described accurately through quantum mechanics. You trace the implications of these conditions on the star's overall stability, learning that the strong nuclear force resists further compression, preventing collapse into a black hole if the mass remains below a certain threshold. The star's magnetic field, initially generated by the motion of charged particles in the progenitor, becomes concentrated during the collapse. Conservation of magnetic flux means that as the radius of the core decreases, the field strength intensifies dramatically. This sets the stage for magnetars, whose magnetic fields will eventually reach strengths billions of times greater than anything achievable on Earth. You can imagine how the rotation and magnetic energy are intertwined, creating a dynamic environment that will evolve over thousands to millions of years. The balance between these forces determines the star's emissions, spin-down rate, and stability. Observing the supernova remnant, you notice the expanding shell of gas and dust moving outward at thousands of kilometers per second. Shock waves heat the surrounding medium, accelerating particles and producing X-rays and radio waves detectable across the galaxy. The remnant interacts with pre-existing clouds of interstellar matter, shaping future sites of star formation. In this quiet yet powerful process, you witness the recycling of cosmic material. Each neutron star remains at the heart of this evolving system, an enduring testament to the life cycle of massive stars. You reflect on the rarity of these events. Only stars above approximately 8 times the mass of the Sun undergo core collapse to produce neutron stars. Within this group, a small fraction will form magnetars, requiring specific conditions of rotation and magnetic field amplification at birth. You consider how these initial differences lead to diverse outcomes in stellar evolution. Even within a single galaxy, the formation of neutron stars is a rare and remarkable occurrence, contributing to the variety of compact objects observed by astronomers. The environment around a newly formed neutron star is extreme. The density and gravity make the surface almost incomprehensible, yet the star is stable. You understand that the outer layers have dispersed, leaving behind a core that quietly carries immense energy. The balance of forces within the neutron star is delicate. The strong nuclear force counteracts gravity, while the residual thermal and rotational energy slowly radiates away. Over time, the neutron star cools, emitting X-rays from its surface and magnetospheric activity. These emissions provide astronomers with insight into its structure and evolution, connecting observations to the theoretical models you have traced. You observe that the neutron star can be found in isolation or within a binary system. In the latter case, interactions with a companion star can alter its evolution through accretion of matter, spinning it up or affecting its magnetic field. Even small differences in mass transfer or orbital parameters can produce significant variations in observable behavior. You see how diverse the life stories of neutron stars can be, each shaped by both initial conditions and environmental influences. In the stillness of space, the neutron star rotates with a silent persistence. You follow its cooling process as thermal energy escapes into the surrounding space. X-ray observations reveal hotspots at the magnetic poles, while the overall surface temperature gradually declines over thousands of years. The magnetic field slowly evolves, and stresses in the crust may develop, hinting at future activity. You sense the continuity of physical processes, the predictable laws of nature that govern these dense remnants and connect them to broader cosmic structures. Every neutron star carries a record of its progenitor, a memory encoded in mass, rotation, and magnetic strength. You understand that by studying these remnants, astronomers can reconstruct the life and death of massive stars. Observations from radio, X-ray, and gamma-ray telescopes allow scientists to measure spin rates, surface temperatures, and magnetic field strengths. You realize that each measurement contributes to a comprehensive understanding of how matter behaves under extreme conditions, providing insight into physics that cannot be reproduced in terrestrial laboratories. As you focus on the quiet persistence of these remnants, you notice the subtle interactions with the surrounding interstellar medium. The neutron star's gravity can influence nearby gas, and its magnetic field can accelerate particles, producing radiation detectable over vast distances. The remnants of the supernova continue to expand, cooling and mixing with other clouds of cosmic matter. You observe how even in apparent stillness, energy and matter continue to circulate, linking the life and death of stars to the broader galactic environment. You feel the immense timescales over which these processes unfold. While a human lifetime is brief, neutron stars exist for millions to billions of years. Their slow cooling, gradual spin-down, and magnetic evolution are all governed by fundamental physical laws. By studying these objects, you connect with the deep timescales of the universe, appreciating the patient unfolding of stellar processes. You recognize that these remnants, quiet yet powerful, are essential markers of cosmic evolution. In the stillness around you, the neutron star persists as a compact, dense relic. It is an extreme laboratory for physics, a bridge between the life of a massive star and the exotic conditions that will eventually produce the most magnetically intense objects in the universe. You sense that within this tiny, ultra-dense sphere, the seeds of magnetic extremity are already present, waiting for conditions that will amplify them into the fields that twist space itself. The quiet persistence of these remnants offers a gentle, enduring window into the mechanics of stars, gravity, and the transformation of matter under the universe's most extreme conditions. You focus your attention on the neutron star, an object that is simultaneously small and extraordinarily massive. Its radius spans only about 20 kilometers, yet it contains more mass than the Sun. You imagine the compression required to condense such a quantity of matter into a volume smaller than a city. Every teaspoon of its material would weigh billions of tons. Gravity on the surface is immense, curving spacetime subtly around it. Light escaping from the surface is redshifted, carrying with it information about the star's density and mass. Observing these properties allows astronomers to calculate both the size and the mass with remarkable precision. Inside the neutron star, matter exists in forms that are almost inconceivable compared to the everyday experience. Atomic nuclei have been crushed together, and electrons have merged with protons to create a dense sea of neutrons. These neutrons are supported by the strong nuclear force, resisting further compression. You note that this force is what prevents the star from collapsing into a black hole, provided the mass does not exceed a critical threshold known as the Tolman-Oppenheimer-Volkoff limit. You feel the subtle balance between gravity pulling inward and nuclear forces pushing outward, a precise interplay that maintains the star's structure. You observe the rotation of the neutron star. Many spin rapidly, completing a full rotation in a fraction of a second to a few seconds. Conservation of angular momentum explains the speed. As the progenitor star collapsed, its radius shrank, and its rotation accelerated. Some neutron stars rotate with astonishing stability, becoming highly precise cosmic clocks known as pulsars. You follow the radiation beams sweeping through space as they rotate, detectable as rhythmic pulses when they cross Earth. The regularity of these pulses is so reliable that they rival atomic clocks in precision. The magnetic field of a neutron star is concentrated and intense. Fields range from millions to trillions of Gauss, vastly exceeding the strongest magnets created on Earth. You notice that the field arises from the motion of charged particles during the star's formation, amplified as the core contracts. This intense magnetism shapes the surrounding space, influencing the acceleration of particles and the emission of electromagnetic radiation. You understand that the magnetic field is not uniform. It is strongest near the magnetic poles, where particle acceleration produces focused radiation detectable across vast distances. You consider the star's surface. While small, it has a solid crust formed of neutron-rich nuclei. This crust is extraordinarily rigid, despite the extreme density. Beneath it, the interior is thought to contain superfluid neutrons and superconducting protons. These states of matter allow frictionless motion and extraordinary magnetic properties. You imagine the interactions between the crust and the interior, which influence rotational stability and may generate observable phenomena such as glitches, sudden changes in rotation rate. These glitches provide scientists with valuable insight into the internal structure and dynamics of the star. The neutron star's environment is shaped by its gravitational and magnetic fields. Space near the surface is warped, bending the paths of light and matter. You observe that atoms and particles approaching the star are influenced by these forces, accelerating to high velocities and emitting radiation as they interact with magnetic fields. The surrounding region becomes a natural laboratory for extreme physics, where the interplay between gravity, nuclear forces, and electromagnetism can be studied through careful observation. You examine the thermal properties of the star. Initially, it is extremely hot, with temperatures reaching millions of degrees at the surface. Over time, the star cools by radiating X-rays, slowly losing thermal energy to space. The cooling rate provides important information about the star's composition and the behavior of matter at nuclear densities. You follow theoretical models that explain this cooling through neutrino emission, conduction through the crust, and surface photon emission. The process unfolds over thousands to millions of years, a gradual and predictable release of energy that can be measured by sensitive instruments. The neutron star's magnetic axis is often misaligned with its rotation axis. This misalignment produces pulsating radiation when the magnetic poles sweep past an observer. You notice how the pulse profile depends on the orientation of the star and the geometry of the magnetic field. Observations of these pulses allow astronomers to infer details about the star's spin, magnetic strength, and even the structure of the crust. You follow the careful measurements that reveal timing variations, pulse shape changes, and sudden glitches, each providing a clue to the star's interior. Interactions with a companion star, when present, can alter the neutron star's properties. Accretion of matter from a companion can increase spin rate or modify the magnetic field. You imagine matter spiraling along magnetic field lines onto the star's surface, releasing energy in X-rays. These interactions are observed in binary systems, where precise timing and spectral analysis provide insight into both stars. The dynamics of mass transfer and magnetic interactions reveal the complexity of stellar evolution beyond isolated neutron stars. You reflect on the population of neutron stars in the galaxy. They are rare but numerous enough to be significant markers of stellar evolution. Observations across radio, X-ray, and gamma-ray wavelengths allow scientists to catalog their locations, spin rates, and magnetic fields. You notice patterns in their distribution, often associated with remnants of supernovae, tracing the history of massive stars in the Milky Way. These remnants continue to enrich the galaxy with heavy elements, linking the neutron star to the broader processes of cosmic evolution. The physics governing neutron stars also intersects with fundamental concepts of relativity. You perceive how the curvature of spacetime affects the star's rotation and emission. Light escaping the gravitational well is shifted to longer wavelengths, a phenomenon known as gravitational redshift. Frame dragging may occur near the surface if the star rotates rapidly, subtly twisting spacetime. You understand that these effects are measurable and provide critical tests of general relativity under extreme conditions, confirming theoretical predictions through observation. You consider the long-term evolution of a neutron star. Magnetic fields decay slowly, rotational energy decreases over time, and thermal emissions fade. The star becomes quieter, though still detectable through sensitive instruments. Some may evolve into magnetars if initial conditions of rotation and field strength are extreme. Others may remain as conventional pulsars or eventually cool to invisibility. You notice how small differences at birth have profound consequences for the observable life of the star. Even in its apparent stillness, the neutron star is a hub of subtle activity. Crustal movements, magnetic decay, and residual thermal energy produce continuous, measurable phenomena. You appreciate how carefully astronomers interpret these signals to understand the underlying physics. Observing these effects requires patience, precision, and careful modeling, linking theoretical predictions to real measurements. The neutron star becomes a window into processes that cannot be reproduced in terrestrial laboratories, demonstrating the extraordinary range of natural conditions in the universe. You reflect on the significance of neutron stars as laboratories of extreme physics. They combine high density, strong gravity, rapid rotation, and intense magnetic fields in a single object. Studying them informs understanding of nuclear physics, electromagnetism, and relativity simultaneously. You sense the interconnectedness of these phenomena, each aspect revealing more about the limits of matter and the fundamental laws that govern the cosmos. The neutron star embodies both the end point of stellar evolution and the beginning of new physical phenomena waiting to be explored. In the quiet of space, the neutron star rotates steadily, its surface hot and magnetic field strong. You realize that within this small, dense remnant lies the potential for even more extreme conditions, where magnetic fields will eventually reach unimaginable strengths and begin to twist the very fabric of spacetime around them. You turn your attention to the most extreme magnetic objects in the universe, magnetars. They begin as neutron stars already dense and compact, but only a select few will develop the extraordinary magnetic fields that define them. The conditions for their formation are precise. The progenitor star must be massive enough to produce a neutron star and must retain rapid rotation during collapse. You notice how even small variations in rotational speed or core structure can determine whether a neutron star will become an ordinary pulsar or an extreme magnetar. As the massive star collapses in a supernova, its core contracts dramatically. Conservation of angular momentum causes the core to spin faster as its radius shrinks. The resulting rotation can reach hundreds of times per second, generating a powerful dynamo effect. Charged particles moving in the core amplify existing magnetic fields. The field strength, initially modest, intensifies rapidly as the dynamo converts kinetic energy of rotation into magnetic energy. You observe that this amplification is self-reinforcing, producing fields that can reach up to 10^1 Gauss, far beyond the capacity of typical neutron stars. The birth of a magnetar is a process of extreme physics. The density of the core ensures that matter is packed into a near-perfect neutron lattice. Neutrons move in highly constrained ways, while superconducting protons allow electric currents to flow with minimal resistance. These currents interact with the rapidly rotating environment, further strengthening the magnetic field. You see that the combination of rotation, superconductivity, and nuclear matter creates conditions unlike anything else in the cosmos. You notice that not all neutron stars undergo this transformation. Most rotate too slowly, or their internal structure does not support an efficient dynamo. Only a small fraction, perhaps 1 in 10,000 massive stars, will produce magnetars. The rarity of these objects emphasizes the delicate balance required during the final moments of a star's life. Even subtle differences in the progenitor's mass, composition, or rotation rate can determine whether it will become a magnetar or a more ordinary neutron star. The magnetic field of a newly formed magnetar dominates its environment immediately. You observe how field lines emerge from the surface, extending far into space. Particles in the surrounding plasma are constrained to follow these lines, producing currents and radiation that mark the star as highly energetic. The field is strongest at the magnetic poles, and its intensity is sufficient to affect atomic structure near the surface. You sense that the magnetar's presence shapes the surrounding space in ways that ordinary neutron stars cannot. As the star spins, the magnetic field interacts with the stellar crust. Stresses develop in the rigid lattice of neutron-rich nuclei. You note that these stresses can fracture the crust, releasing energy in the form of X-ray or gamma-ray bursts. Early in the magnetar's life, these flares may occur frequently, driven by the evolving magnetic field. Each burst is a consequence of fundamental physics, the rearrangement of magnetic structures and the adjustment of the crust under extreme pressure. The energy released in a single flare can exceed that of the sun over hundreds of thousands of years, concentrated into a moment that travels across the galaxy. You follow the evolution of the magnetar's rotation. Rapidly spinning at birth, the star loses rotational energy through electromagnetic radiation. Magnetic braking slows the rotation over decades or centuries. The magnetic field, initially amplified by rotation, begins to decay as energy is dissipated. You observe that this decay is gradual, influencing the star's emissions and thermal structure over thousands of years. The interplay between rotation and magnetic energy defines the magnetar's observable behavior throughout its early life. The internal structure of the magnetar plays a critical role in sustaining its magnetic intensity. Superfluid neutrons in the interior move without friction, allowing angular momentum to redistribute smoothly. Superconducting protons maintain strong electric currents, supporting the magnetic field against decay. The crust, while rigid, is flexible enough to respond to internal stress, producing measurable phenomena. You notice that this combination of extreme states of matter is unique to magnetars, creating conditions impossible to reproduce on Earth. Observationally, magnetars are recognized through their high-energy emissions. X-rays and gamma rays dominate, produced by particle acceleration along magnetic field lines. You understand that these emissions provide critical information about the field's strength and configuration. Variations in pulse timing, flare intensity, and spectrum allow scientists to infer properties of the magnetic field, rotation rate, and surface structure. Through these observations, the theoretical models of magnetar formation and evolution are confirmed and refined. You consider the relationship between progenitor mass and magnetar formation. Stars above approximately 20 solar masses are most likely to produce magnetars, provided rapid rotation is maintained during collapse. You observe that mass loss through stellar winds or interaction with a companion can influence the final core rotation. Even the metallicity of the star, affecting opacity and wind strength, can play a role in determining whether the core collapses into a highly magnetized neutron star. These subtle dependencies illustrate the delicate conditions required for magnetar birth. The magnetar's surface is extraordinarily active during its early life. Magnetic stress induces movement in the crust, generating thermal and electromagnetic emissions. Hotspots develop near magnetic poles, radiating X-rays detectable across the galaxy. You see that these emissions vary with rotation, producing characteristic pulsations. The combination of magnetic decay, rotational slowdown, and crustal stress defines the magnetar's dynamic behavior over centuries. Each observed flare or pulse is a direct consequence of physics at the limits of density, magnetism, and rotation. The energy stored in the magnetic field of a magnetar is immense. You calculate that a single magnetar may contain more energy in its field than the total rotational energy of an ordinary neutron star. This energy reservoir can power dramatic events, including giant flares, sudden bursts, and persistent X-ray emission. You understand that the field influences both the star's internal dynamics and its interaction with surrounding space. Plasma, gas, and radiation respond to the field, producing phenomena that reveal the magnetar's presence even at immense distances. Even as the magnetic field gradually decays, the processes set in motion during formation continue to influence the star. You observe how currents in the interior shift, stress accumulates in the crust, and high-energy particles are accelerated along field lines. The magnetar's life is a continuous interplay between energy storage, dissipation, and emission. These processes follow predictable physical laws, yet manifest in extraordinary and extreme ways. By studying them, astronomers gain insight into the limits of matter, magnetism, and nuclear physics. You notice the broader cosmic context. Magnetars are rare, yet they provide a bridge between massive stellar evolution, nuclear physics, and high-energy astrophysics. Their existence informs understanding of supernova mechanisms, stellar rotation, and the amplification of magnetic fields. Observing their emissions allows for precise measurement of fundamental forces, testing models of matter under extreme density, temperature, and magnetic intensity. You appreciate the precision and complexity of these natural laboratories. The birth of a magnetar represents the convergence of density, rotation, and magnetic amplification. You see that only under the right conditions can a neutron star achieve magnetic fields strong enough to influence spacetime and drive high-energy phenomena. This transformation is rare, yet it follows the predictable laws of physics. You sense the continuity from the collapse of a massive star to the emergence of an object whose magnetic field will dominate its environment and reveal new aspects of extreme physics. You focus on the magnetic field that defines the magnetar, recognizing it as one of the strongest forces in the universe. At birth, the field may reach 10 to 15 orders of magnitude stronger than the sun's magnetic field, far exceeding any artificial field produced on Earth. You sense the scale. A field of this intensity can affect atoms, alter particle motion, and dominate the behavior of surrounding plasma. The strength is sufficient to distort electron orbitals, influence nuclear processes, and shape radiation emission. Every aspect of the magnetar's environment is influenced by this extraordinary magnetism. The magnetic field originates from the star's rapid rotation and internal currents. Charged particles moving within the highly conductive interior generate currents that amplify the field through a dynamo effect. You notice how small differences in rotation or core composition at birth can produce significant variations in field strength. Some magnetars exhibit fields strong enough to bend light and accelerate particles to relativistic speeds. This magnetic dominance sets them apart from other neutron stars and defines the interactions between the star and its surroundings. You observe how the field extends outward from the magnetar, forming complex structures. Near the surface, it is strongest at the magnetic poles, creating channels that guide particle motion. Charged particles spiral along these field lines, producing high-energy radiation observable as X-rays and gamma rays. Farther from the star, the field weakens but continues to influence the interstellar medium, shaping plasma flows and altering particle trajectories. You see that the magnetosphere is a dynamic environment, continuously responding to changes in the magnetic field and the star's rotation. The intensity of the magnetic field also affects the star's surface. The crust experiences stresses that can fracture the rigid lattice of neutron-rich nuclei. These fractures release energy in the form of bursts or flares, a direct consequence of the magnetic field's strength. You realize that the field is responsible for both the continuous emissions and the sudden, dramatic events that define magnetar behavior. Each emission carries information about the internal structure, the crust, and the arrangement of the magnetic field. At the atomic level, the magnetic field produces extreme effects. Electrons are confined in their motion perpendicular to the field lines, altering the shape of atomic orbitals. In such strong fields, atoms can become elongated along the direction of the field, modifying their physical and chemical properties. You notice that these conditions cannot be replicated in laboratories on Earth, yet they occur naturally around the magnetar. The behavior of matter under these conditions provides insight into physics at extremes, revealing interactions that are otherwise inaccessible. You examine the field's impact on radiation. Photons moving near the surface interact with the magnetosphere, experiencing processes such as vacuum birefringence, where the vacuum itself becomes polarized in response to the intense field. Radiation emitted from the surface can be absorbed, scattered, or redirected by the magnetic environment. These effects produce characteristic signatures in X-ray and gamma-ray spectra, allowing astronomers to measure the field's strength and geometry with precision. You sense that the field's influence extends far beyond the immediate surface of the star. The evolution of the magnetic field is gradual but continuous. Initially, the field is amplified by rotation, but over thousands of years, it decays through processes such as ohmic dissipation and Hall drift. You observe that the decay rate depends on the internal conductivity, the structure of the crust, and the interactions between superfluid and superconducting components. As the field weakens, the star's emission properties evolve, producing a long-term pattern of high-energy radiation followed by gradual dimming. This decay also affects the likelihood of starquakes and flares, linking internal magnetic processes to observable phenomena. You consider the energy stored in the magnetic field. A single magnetar may contain more magnetic energy than the sun radiates over 1 million years. This energy is available to power bursts, flares, and persistent high-energy emission. You realize that the magnetic field is both a stabilizing and a driving force. It supports the star structurally while also serving as a reservoir of energy for extreme astrophysical events. The interplay between energy storage and dissipation is central to understanding magnetar behavior. The magnetic field also shapes the interaction with surrounding matter. Gas and plasma near the magnetar are forced to follow field lines, accelerating to high velocities. You notice that particles moving in the magnetosphere generate synchrotron radiation, emitting energy across the electromagnetic spectrum. The field acts as both a guide and a constraint, determining the pathways and energies of charged particles. Observations of these emissions provide insight into the field's geometry, strength, and evolution. Magnetars exhibit variability in their magnetic activity. Sudden rearrangements of the field, often triggered by stress in the crust, produce flares detectable across the galaxy. You follow the physics of these events, understanding that they are driven by the realignment of magnetic loops and the release of stored energy. These flares are rare but extremely powerful, illustrating the extreme conditions created by the magnetic field. Even in apparent calm, the field continues to influence the interior and exterior of the star, preparing the environment for future events. The field's influence on rotation is also significant. Magnetic braking transfers rotational energy into electromagnetic radiation, gradually slowing the spin of the star. You observe how the rotation period lengthens over decades and centuries, with the loss of kinetic energy contributing to magnetic decay and particle acceleration. This slow evolution is measurable, providing a precise chronometer for the star's age and magnetic history. By tracking rotation, astronomers can reconstruct the star's life cycle and anticipate future activity. You consider how the field interacts with relativistic effects. Strong gravity near the surface bends light and affects particle motion, while the magnetic field guides charged particles along curved paths. In combination, these effects produce emissions that carry detailed information about the star's structure and spacetime environment. You see that magnetars are natural laboratories for studying physics at the intersection of electromagnetism, quantum mechanics, and general relativity. Even distant from the star, the magnetic field influences space. Plasma, cosmic rays, and interstellar gas respond to the field structure, altering the dynamics of the local environment. You notice that magnetars can energize surrounding nebulae and affect the propagation of high-energy particles. Observing these effects allows astronomers to measure both the immediate and extended influence of the magnetic field, connecting local observations to the broader galactic context. The magnetic field is central to the magnetar's identity. Its intensity, structure, and evolution govern emissions, crustal behavior, particle acceleration, and interactions with the surrounding space. You realize that understanding these fields is essential for interpreting observations and for modeling the physics of ultradense matter. Each measurement of pulse timing, flare intensity, or X-ray spectrum provides a window into the extreme environment defined by magnetism. You reflect on the broader significance of these fields. By studying magnetars, scientists gain insight into the limits of magnetic strength, the behavior of matter under extreme forces, and the interplay between magnetism and spacetime. These observations extend knowledge of fundamental physics beyond the reach of terrestrial experiments. You sense the precision and consistency of natural laws, even under conditions far removed from everyday experience. You feel the quiet power of the magnetic field as it dominates the star and shapes its surroundings. Its influence extends from the crust to the magnetosphere, guiding particles, producing radiation, and storing energy over millennia. Every observation of a magnetar carries evidence of this field, providing a direct measure of nature's capacity for extreme forces. You recognize the field as both a stabilizing structure and a source of energetic activity, quietly governing the star's behavior in ways that are both measurable and extraordinary. You focus on the rotation of a magnetar, a motion that carries both energy and influence. At birth, some magnetars spin hundreds of times per second, their compact mass amplifying angular momentum through collapse. You notice how rapid rotation contributes to the initial amplification of magnetic fields, feeding energy into the star's magnetosphere. Over time, however, the intense magnetic field acts as a brake, gradually slowing the spin. This magnetic braking converts rotational energy into electromagnetic radiation, particle acceleration, and heat in the crust. The rotational period of a magnetar is typically longer than that of ordinary pulsars, ranging from 2 to 12 seconds. You see that this slower rotation is a direct consequence of the star's immense magnetic field. The field exerts torque on the star's crust and magnetosphere, transferring energy outward and producing X-rays and gamma rays. These emissions are continuous yet subtle, a slow shedding of rotational energy that can be measured by sensitive instruments. You understand that even in apparent stillness, the star's rotation is dynamic, influencing both its interior and surroundings. You observe the effects of rotational slowdown over time. As the magnetar loses angular momentum, its period gradually increases. You notice that the spin-down rate is closely linked to the field strength. Stronger fields decelerate the star more rapidly. Measurements of this process allow scientists to estimate both age and magnetic intensity. You follow timing observations of pulses, noting how each rotation is recorded as a small increment in time, providing precise data about the star's evolution. The rotational energy is substantial, yet it is only a fraction of the energy stored in the magnetic field. You calculate that even as the spin slows, the magnetar retains immense energy capable of powering high-energy emissions. You see that this interplay between rotation and magnetism defines the star's behavior over centuries. The balance is delicate. Rotation drives initial field amplification, while the magnetic field gradually transfers energy outward, shaping emissions and surface activity. You consider the interior dynamics that contribute to rotational stability. Superfluid neutrons within the core allow angular momentum to redistribute smoothly, reducing internal friction. This superfluid component interacts with the rigid crust, producing occasional irregularities in rotation known as glitches. These sudden changes in spin provide a glimpse into the internal structure, revealing the coupling between crust and core. You realize that even small rotational variations carry meaningful information about the magnetar's interior. The magnetar's magnetic axis is often misaligned with its rotational axis. This misalignment causes radiation emitted from the magnetic poles to sweep across space, producing observable pulsations. You follow the periodicity of these pulses, recognizing them as indicators of both rotation and field orientation. The pulse profile can vary over time, reflecting changes in the crust, magnetosphere, or alignment. By studying these variations, astronomers gain insight into the evolving geometry and dynamics of the star. You notice that the spin-down rate is not uniform. Interactions between the crust, magnetic field, and interior currents create subtle variations. Some magnetars experience temporary accelerations or slower decays in rotation, often linked to magnetospheric changes or crustal movements. You sense the precision required to measure these effects, understanding that each variation carries evidence of complex physical processes within and around the star. The loss of rotational energy contributes to observable phenomena. As the magnetar spins down, energy is converted into radiation and particle acceleration. You observe how this energy is radiated in X-ray and gamma-ray bands, often concentrated near the magnetic poles. Even the smallest transfer of rotational energy can produce detectable changes in emissions. You understand that rotation and magnetic decay are intimately connected, shaping the behavior and observational signature of the magnetar over its lifetime. You reflect on the implications of slow rotation for long-term evolution. A magnetar that begins with a fast spin gradually transitions to a slower state, reducing the rate of magnetic amplification. You notice that this slowdown can influence the frequency and intensity of flares and bursts. The timing of emissions is linked to both rotation and magnetic field configuration, providing a natural clock for studying the star's internal and external processes. You see that rotation is a subtle, persistent driver of magnetar activity. Interactions with surrounding material can also influence rotation. If a magnetar is in a binary system or embedded in dense interstellar plasma, angular momentum can be transferred. Accretion of matter may slightly increase spin rate, while magnetic coupling with charged particles can produce additional torque, modifying spin-down rates. These effects are generally small compared to intrinsic magnetic braking but can provide measurable deviations in pulse timing, adding complexity to observational data. The rotational period provides insight into the magnetar's age. Younger magnetars often rotate more rapidly, while older ones have slowed due to magnetic braking. You notice that by measuring spin period and spin-down rate, astronomers can estimate the star's evolutionary stage. This method, combined with observations of emission patterns and magnetic field strength, allows for a comprehensive understanding of the star's life cycle, linking rotation to magnetic evolution and high-energy phenomena. You consider the energy budget of the magnetar. While rotation contributes significantly at birth, over centuries the magnetic field becomes the dominant source of energy for high-energy emissions. You see that the slow, steady loss of rotational energy is a natural consequence of the star's magnetic intensity, creating a predictable pattern of emission and spin-down. This ongoing interaction between rotation and magnetic forces defines the magnetar's behavior, even in periods of apparent calm. You observe that rotational irregularities, such as glitches, provide a rare opportunity to study the interior dynamics. Sudden changes in spin reveal interactions between superfluid and crust, allowing scientists to model internal structure. You notice how timing observations capture these events with extreme precision, revealing the hidden processes at play beneath the surface. The combination of rotation, magnetic braking, and internal physics creates a complex, yet measurable, portrait of the star. Even as the star slows, the interplay of rotation and magnetic field continues to shape its environment. You notice particle acceleration along field lines, thermal emission from hotspots, and occasional bursts related to crustal stress. Each phenomenon is connected to the star's spin and the distribution of magnetic energy. You sense that rotation, although gradually decreasing, remains a central driver of activity and observational features. The magnetar's rotation, though imperceptible to human senses, governs much of its behavior. From the timing of pulses to the acceleration of particles, spin provides both energy and structure. You see that the magnetic field and rotation are intertwined. The field slows the spin, and the spin originally amplified the field. This relationship continues for thousands of years, a quiet, persistent dialogue of forces that determines how the magnetar interacts with its surroundings. You reflect on the quiet yet dynamic nature of this rotation. Each pulse, each subtle change in spin, carries information about both the interior and exterior of the magnetar. The gradual loss of angular momentum is a predictable and measurable phenomenon, revealing the physical laws governing dense matter, magnetism, and extreme gravitational fields. You sense the precision and stability of these cosmic processes, unfolding slowly over centuries. You turn your attention to the light that emerges from the magnetar, not in visible wavelengths, but in X-rays and gamma rays. These high-energy photons are the primary signals through which astronomers detect and study magnetars. You notice that the emissions arise directly from the interaction between the star's immense magnetic field, its rotation, and the structure of its surface. The surface is hot, with temperatures of millions of degrees, and the field channels charged particles along curved trajectories, accelerating them to near-light speeds. The magnetar's magnetic poles are regions of particular activity. You observe particles spiraling along field lines, emitting synchrotron radiation as they accelerate. The curvature of these lines forces the particles to move in arcs, producing photons in the X-ray and gamma-ray bands. You notice that this process is continuous, generating a persistent glow that can be measured across great distances. Even the faintest variation in the field or rotation can alter the intensity and spectrum of the emitted radiation. Occasionally, stress in the crust produces sudden bursts of energy. These events, sometimes called flares or starquakes, occur when magnetic pressure fractures the rigid lattice of neutron-rich nuclei. You see that the energy released in a single flare can exceed the total energy output of the Sun over hundreds of thousands of years. The photons generated in these bursts travel across the galaxy, arriving at Earth as brief, intense flashes. Observing these flares provides direct evidence of the magnetic and structural dynamics within the star. The magnetosphere plays a crucial role in shaping emissions. Particles trapped within the magnetic field can be accelerated repeatedly, emitting high-energy photons at multiple wavelengths. You observe that the density and configuration of plasma near the star influence the emission spectrum. Changes in field alignment or crustal activity create variations in intensity and timing, producing complex patterns detectable by space-based observatories. Each measurement allows scientists to reconstruct the star's environment and magnetic geometry. Thermal radiation from the surface also contributes to the X-ray output. You notice hotspots near the magnetic poles, where field-aligned currents deposit energy into the crust. These regions are significantly hotter than the surrounding surface, producing concentrated X-ray emission. Over time, the distribution of hotspots evolves as magnetic stresses shift and the star cools. You observe that tracking these variations provides a detailed understanding of energy transfer, magnetic field decay, and surface composition. Gamma-ray emission is particularly dramatic. You observe particles accelerated along field lines reaching extreme velocities, producing photons in the highest energy bands. These photons can escape the magnetosphere, carrying information about the field's strength and orientation. Giant flares, rare but exceptionally powerful, release tremendous amounts of gamma radiation in seconds. You notice that these events are among the most energetic phenomena in the galaxy, yet they follow predictable physical laws dictated by magnetic reconnection and energy storage in the star's crust. You consider the propagation of these high-energy photons through space. X-rays and gamma rays are absorbed or scattered less than lower-energy light, allowing them to travel vast distances with minimal interaction. This means that even a magnetar thousands of light-years away can be detected and analyzed. You notice that careful measurement of pulse timing, spectrum, and intensity provides precise data about rotation, magnetic field strength, and crustal activity. Observations from satellites and space telescopes make these measurements possible, revealing the otherwise hidden activity of the star. Magnetic field decay also contributes to emissions. As the field gradually weakens, energy is released into the crust and magnetosphere. This energy powers both persistent radiation and smaller bursts. You notice that the decay rate can be estimated by monitoring changes in luminosity and pulse characteristics. The slow transformation of magnetic energy into radiation over centuries demonstrates the continuous and dynamic processes operating within the magnetar, even when it appears stable from a distance. You observe that the timing of pulses provides additional insight. The rotational period, combined with the location of magnetic poles, produces periodic variation in X-ray and gamma-ray intensity. These pulses are precise, allowing astronomers to track rotational slowdown, glitch events, and changes in magnetic field structure. You notice that even subtle deviations in pulse timing reveal interactions between the crust and interior superfluid, offering a window into the star's internal dynamics. Particle acceleration near the magnetar's surface produces additional phenomena. Electrons and positrons move along field lines, emitting curvature radiation and contributing to the high-energy spectrum. You see that interactions between these particles and the surrounding magnetosphere can produce secondary emissions, creating a complex, multi-wavelength signal. Observing these emissions helps scientists map the magnetic topology and energy distribution, confirming models of field decay, particle acceleration, and energy dissipation. Flares and bursts are also influenced by the star's rotation. You notice that misalignment between rotation and magnetic axes determines how energy is released in sudden events. The field stores energy unevenly, with localized concentrations near the poles or crustal fractures. When stress exceeds the crust's structural limit, energy is released in a rapid, observable burst. You recognize that this mechanism links magnetic structure, rotation, and surface dynamics in a coherent physical process. Persistent X-ray emission provides a long-term measure of magnetar activity. You observe that, even without flares, the star emits steadily due to a combination of thermal radiation, particle acceleration, and magnetic dissipation. This glow offers a continuous signal that can be measured over decades. Monitoring this emission allows scientists to track field decay, rotational slowdown, and surface temperature changes, constructing a timeline of magnetar evolution. The study of X-rays and gamma rays from magnetars illuminates fundamental physics. You see that particle motion, magnetic reconnection, radiation emission, and energy dissipation occur under extreme conditions not reproducible on Earth. Observing these processes provides insight into nuclear physics, magnetohydrodynamics, and relativistic effects. You realize that each photon carries a message about forces and interactions that would otherwise remain hidden, making magnetars natural laboratories for high-energy astrophysics. Even the interstellar environment is affected by emissions. You notice that particles ejected from flares and accelerated along field lines can interact with surrounding gas and plasma, producing secondary radiation or influencing local particle populations. The magnetar's activity has a measurable impact on its immediate neighborhood, connecting the star to broader galactic processes. You observe that even isolated magnetars subtly shape their cosmic surroundings through high-energy emissions. The interplay between magnetic energy, rotation, and radiation defines the magnetar's observable behavior. You follow the flow of energy from the interior to the surface and outward into space. Each process, particle acceleration, crustal stress, magnetic decay, rotation, is linked, producing a coherent pattern of emissions. By studying these signals, scientists reconstruct the extreme conditions within the star and test models of matter under high density, strong magnetism, and rapid rotation. You reflect on the consistency of these processes. Despite the extreme nature of the star, its emissions follow predictable physical laws. Flares occur when stress thresholds are exceeded, rotation gradually slows, and radiation is emitted according to well-understood mechanisms. You notice that careful observation and measurement allow scientists to understand phenomena that are both extraordinary in scale and precisely quantifiable. The high-energy photons emitted by magnetars provide a direct line of information across the galaxy. You sense the continuity of this energy transfer, from the interior and crust to the magnetosphere and beyond. Observing X-rays and gamma rays allows astronomers to study processes that are otherwise invisible, revealing the structure, dynamics, and evolution of these extreme stars. You focus on the surface of the magnetar, a thin crust of neutron-rich nuclei that covers an ultradense interior. Though incredibly rigid, this crust is not immune to the forces generated by the star's intense magnetic field. You notice that the field lines thread through the crust, exerting pressure and creating stress over centuries. These stresses accumulate slowly, and when the structural limit of the crust is exceeded, the result is a sudden fracture, a starquake. The fractures are analogous to tectonic events on Earth, though under incomparably more extreme conditions. You observe that the forces acting on the Magnetars crust are many orders of magnitude greater than anything experienced on a planet. The density of matter, combined with magnetic pressure, allows only minimal deformation before energy is released. Unlike earthquakes, these starquakes release energy directly into the magnetosphere, accelerating particles and producing intense bursts of X-rays and gamma rays. You notice that starquakes are often linked to the evolution of the magnetic field. As the field slowly decays or rearranges itself, magnetic tension within the crust builds. Small shifts may occur continuously, but larger fractures produce sudden, measurable events. These bursts are observable across the galaxy, allowing astronomers to study the internal dynamics indirectly. You sense that even a brief flare carries information about the crust's composition, rigidity, and interaction with the magnetic field. The process begins deep in the crust, where the neutron lattice is compressed to extreme densities. Magnetic forces push and pull on localized regions, creating stress concentrations. You follow the buildup of energy as it reaches a critical threshold, where the crust can no longer maintain structural integrity. At this moment, the lattice fractures, releasing energy in milliseconds. This sudden release produces a shock that propagates through the crust and into the magnetosphere, driving the acceleration of charged particles. Particle acceleration along the magnetic field lines produces high-energy radiation. Electrons and positrons spiral at nearly the speed of light, emitting synchrotron radiation in X-ray and gamma-ray bands. You observe that the spectrum of this emission depends on the local field strength and the geometry of the fracture. The most intense starquakes can release more energy in a fraction of a second than the sun emits in tens of thousands of years, a testament to the extreme conditions of the Magnetars crust. Even smaller fractures have observable effects. You notice that minor starquakes can slightly alter the rotation rate, producing measurable glitches. These changes in spin reveal the coupling between the crust and the superfluid interior. By monitoring these rotational variations alongside high-energy emissions, scientists can infer details about both the crust and the deeper layers of the star. Each observation provides a window into the processes occurring far beneath the surface. The magnetic field plays a central role in both initiating and shaping starquakes. You see that the field is not uniform. Twisted loops and localized concentrations create regions of higher stress. When these areas fracture, the resulting emission is often focused along specific magnetic pathways. The location and intensity of flares correspond to the topology of the field, allowing researchers to map its structure through careful observation. You notice that the frequency of starquakes varies. Younger magnetars with stronger fields experience more frequent and energetic events, while older stars exhibit less intense activity as the field decays. This gradual change provides insight into the life cycle of the star and the evolution of its magnetic field. By comparing activity across different magnetars, scientists can construct models linking age, field strength, and crustal behavior. Thermal energy also contributes to crustal stress. You observe that hotspots develop where magnetic currents deposit energy, locally heating the crust. Temperature gradients create expansion and contraction, adding to mechanical stress. The combination of thermal and magnetic pressures determines the timing and intensity of fractures. Understanding this interplay helps explain variations in flare activity, from minor bursts to catastrophic events. Starquakes have effects beyond the immediate surface. You notice that the sudden release of energy propagates into the magnetosphere, inducing currents and particle acceleration. Charged particles emit radiation across the electromagnetic spectrum, producing observable signals even thousands of light-years away. You sense the connectivity between the internal fracture and the external environment, demonstrating that events within the crust influence the surrounding space. The energy budget of starquakes is substantial. You calculate that a single event may release 10 to 10 ergs of energy, equivalent to the total energy output of the Sun over tens of thousands of years. This energy powers flares, accelerates particles, and heats localized regions of the crust. You observe that the repetition of these events over centuries contributes to the Magnetars' evolving high-energy signature. Each starquake leaves an imprint, recorded in timing, spectrum, and intensity of emissions. Even in periods of apparent calm, stress continues to accumulate. You notice that the crust responds elastically to small shifts in the magnetic field, maintaining structural integrity until thresholds are exceeded. This slow accumulation of tension is a continuous process, shaping the long-term behavior of the star. By observing subtle changes in emission patterns, scientists can detect precursors to larger starquakes, gaining insight into the internal mechanics of the crust. Glitches in rotation are directly tied to starquakes. You observe that a sudden crustal fracture can slightly redistribute angular momentum, producing measurable changes in spin. These glitches, though small, provide critical data on the interaction between the crust and the superfluid interior. You sense that monitoring both rotational and high-energy emission variations allows a detailed understanding of the coupling between magnetic, structural, and rotational dynamics. The propagation of energy through the crust is influenced by its composition and structure. You notice that areas of higher neutron density or localized impurities alter the path of stress propagation, affecting the size and intensity of flares. Observations of these variations provide indirect evidence of internal heterogeneity, revealing the complex nature of matter under extreme density. You realize that each event is a natural experiment in nuclear and solid-state physics. You reflect on the relationship between magnetar age, field strength, and starquake activity. Younger, highly magnetized stars experience frequent, energetic events, while older, slower magnetars produce smaller, less frequent bursts. This evolution demonstrates the gradual decay of magnetic energy and the adaptation of the crust over time. Observing multiple stars allows scientists to piece together patterns, providing a statistical understanding of crustal stress and high-energy phenomena. Even distant bursts carry information across the galaxy. You notice that gamma-ray and X-ray flares travel without significant absorption, allowing precise timing and measurement. These signals are analyzed to infer rotation rate, field strength, and stress distribution. You understand that starquakes are not only dramatic events but also essential probes of the magnetar structure and dynamics. Each flare is a messenger of the extreme physical conditions within the star. You consider the broader implications of starquakes. They demonstrate the interaction of magnetic fields, rotation, and ultradense matter in real time. By studying these events, scientists test models of nuclear physics, superconductivity, and magnetohydrodynamics. You sense that the starquakes are both natural outcomes of extreme conditions and valuable sources of information about fundamental physics at scales and intensities impossible to replicate on Earth. You focus on the environment immediately surrounding the magnetar, where gravity is intense and spacetime itself curves noticeably. The mass of the neutron star, compressed into a sphere just tens of kilometers across, produces a gravitational field billions of times stronger than Earth's. You notice how any nearby matter, from residual supernova debris to interstellar gas, experiences this gravity as an almost irresistible pull. Particles move along the curved paths of spacetime, following geodesics determined by the star's compact mass. The curvature of spacetime near the magnetar affects light as well. Photons emitted from the surface follow curved trajectories, producing gravitational lensing effects. You sense that the star's intense field can bend light from hotspots or flares, slightly altering their apparent position to distant observers. This bending is not large enough to distort the star's overall appearance drastically, but it is measurable, allowing astronomers to confirm the star's mass and radius indirectly. Rotation introduces additional relativistic effects. As the magnetar spins, it drags spacetime along with it, a phenomenon known as frame dragging. You observe that matter in close orbit does not move in perfect Newtonian paths. Instead, it precesses in response to the star's rotation. Even photons feel the subtle twisting of spacetime, altering their path slightly before escaping the gravitational pull. These effects are most pronounced near the star's surface, diminishing with distance but still significant for matter and radiation in the immediate magnetosphere. The Magnetar's magnetic field also interacts with spacetime, though indirectly. You notice that electromagnetic forces dominate the motion of charged particles, guiding them along field lines while gravity curves the background space. The combined effect produces complex trajectories where both forces must be considered. Electrons spiraling near the magnetic poles move in helical paths, while gravity subtly alters their overall motion. You sense that the interplay of magnetism and relativity creates a uniquely constrained environment, one in which extreme physics can be observed in action. You follow the motion of infalling matter. Gas clouds or debris fragments that approach the star are accelerated along curved paths. Near the surface, tidal forces stretch and compress material due to intense gravitational gradients. These forces can strip electrons from atoms and heat plasma to millions of degrees. Radiation emitted from these interactions carries imprints of both gravity and magnetic structure, allowing astronomers to decode conditions near the magnetar from light years away. Time behaves differently near the star. You observe that clocks closer to the surface tick more slowly relative to those far away, a consequence of gravitational time dilation. Even a brief observation of emitted photons reveals slight frequency shifts due to this effect, measurable as gravitational redshift. You sense that spacetime near the magnetar is dynamic, influencing not only the paths of matter and light but also the flow of time itself. High-energy particles within the magnetosphere are influenced simultaneously by gravity and magnetism. Electrons and ions accelerated along field lines experience relativistic velocities, and their motion is subtly modified by the curvature of spacetime. You notice that synchrotron radiation emitted from these particles carries signatures of both velocity and gravitational effects. Observing these photons allows scientists to reconstruct conditions in the magnetosphere with remarkable precision, mapping the interaction of magnetic and relativistic forces. Magnetars also produce frame-dragging effects on orbiting debris. You consider that even compact remnants from the progenitor supernova can have their orbits altered gradually. Small changes in angular momentum occur due to the twisting of spacetime, resulting in precession over time. You see that these motions, though subtle, are detectable with long-term observations, providing evidence for relativistic corrections to classical orbital mechanics. You notice that relativistic effects are intertwined with rotational energy loss. As the star spins down due to magnetic braking, the energy radiated in high-energy photons is influenced by both gravity and rotation. Light emitted from hotspots experiences gravitational redshift and bending, while magnetic energy determines particle acceleration and emission intensity. The combination creates complex observational signatures that encode information about mass, spin, magnetic field, and spacetime curvature. Nearby matter is affected in ways that can be modeled precisely. Plasma in the magnetosphere moves along constrained field lines, but its overall trajectory is curved by the star's gravity. You follow the motion of electrons and ions as they spiral, accelerated by magnetic tension and influenced by gravitational gradients. Observing these paths provides a unique opportunity to study physics in the regime where strong gravity and ultra-strong magnetic fields coexist. You consider the emission of bursts and flares in the context of relativistic physics. Photons leaving the surface must climb out of the gravitational well, slightly reducing their energy. At the same time, the magnetic field directs the motion of particles emitting these photons, producing beaming effects. You realize that the timing, spectrum, and intensity of emissions are determined by a combination of spacetime curvature and magnetic forces, allowing precise modeling of the star's environment. The neutron star's interior is affected by relativity as well. You note that the dense core produces strong pressure and gravitational gradients. General relativity predicts that internal density, pressure, and mass distribution influence the external field and observable phenomena. You observe that rotational flattening, combined with frame dragging, modifies the local gravitational potential. The structure of the interior, though hidden, is thus indirectly accessible through careful observation of emission patterns, rotation, and orbital effects on nearby matter. Even photons traveling far from the magnetar carry information about spacetime. Light curves from flares and periodic pulses encode time dilation, gravitational redshift, and lensing effects. You sense that the universe allows you to read these subtle imprints, providing an indirect but accurate picture of the star's mass, spin, and magnetic geometry. Each measurement reinforces the precise relationship between matter, magnetism, and the curvature of spacetime. Interactions between magnetism and gravity also influence particle acceleration. Electrons moving at relativistic speeds in the magnetosphere experience not only magnetic forces but also curvature of spacetime that subtly alters trajectory and energy distribution. Radiation from these particles thus encodes information about both magnetic intensity and gravitational potential. You realize that the combination produces a natural laboratory for studying physics in regimes impossible on Earth. You reflect on the environment near the magnetar as a balance of forces. Gravity curves space, magnetism guides particles, and rotation introduces relativistic effects. Observations of light, particle motion, and emissions allow scientists to quantify each component. You sense that, although extreme, these processes are governed by the same physical laws that operate across the universe, providing continuity between ordinary space and the intense conditions near a magnetar. You notice that relativistic precession, frame dragging, and magnetic influence are not merely theoretical. Each is measurable through pulse timing, spectral shifts, and flare behavior. By carefully analyzing these signals, scientists reconstruct the geometry and dynamics of both the magnetosphere and the curved spacetime around the star. You sense the precision and subtlety required to interpret these observations, appreciating how extreme physics produces detectable, understandable outcomes. The interface of magnetism and spacetime reveals both the limits of observation and the richness of physical laws. You understand that magnetars provide a unique opportunity to study interactions between dense matter, extreme magnetism, and general relativity simultaneously. Even in quiet periods, the star subtly warps its surroundings, affecting matter, light, and time. These effects are not dramatic in appearance, but they are profound in implication. You begin by considering the fundamental challenge of observing a magnetar. It emits almost no visible light. Its high-energy emissions, primarily X-rays and gamma rays, are invisible to the human eye. You notice that detecting these photons requires specialized instruments in space, beyond Earth's atmosphere, where radiation cannot be absorbed or scattered. Observatories like Chandra, XMM Newton, and Swift are positioned to capture these elusive signals, recording photons with precise energy, time, and location information. Each detection begins with a photon striking a sensitive detector. You observe how X-ray instruments use arrays of silicon or other semiconductor detectors to convert incoming radiation into electrical signals. These signals are then time-stamped and recorded, providing information about the photon's energy and arrival time. You notice that the precision of timing is critical. It allows scientists to determine rotation periods, detect bursts, and analyze subtle variations in emissions over time. Gamma-ray detection is even more complex. You notice that instruments like Fermi or integral use scintillators or coated aperture masks to capture high-energy photons. These devices convert gamma rays into visible flashes or electronic signals that can be counted and measured. Each detection contributes to a detailed map of high-energy activity in the galaxy, revealing flares, bursts, and persistent emission from magnetars. You sense that this process requires extreme sensitivity and careful calibration to distinguish real signals from background noise. Observing a magnetar also requires understanding its rotation. You follow the timing of pulses, which are generated as radiation sweeps past aligned magnetic poles. By recording the interval between pulses, astronomers can measure the rotational period with extraordinary accuracy. You notice that small deviations from perfect periodicity, called glitches, indicate changes in the star's interior, providing indirect information about superfluid dynamics and crustal interactions. Each pulse is a precise marker of time, linking surface and interior physics to observable signals. Spectral analysis adds another layer of insight. You observe that the energy distribution of photons carries information about surface temperature, magnetic field strength, and particle acceleration. By plotting intensity versus energy, astronomers can identify emission components, distinguish thermal radiation from magnetospheric processes, and detect the presence of hotspots. You notice that even small variations in spectral shape can reveal significant physical changes, such as magnetic reconnection or crustal heating. Localization of a magnetar is achieved through triangulation and imaging. X-ray telescopes produce high-resolution images, allowing astronomers to pinpoint sources within supernova remnants or dense star fields. You observe that accurately locating a magnetar enables the study of its environment, associations with stellar populations, and connection to past supernova events. Knowing the position also allows for multi-wavelength follow-up, including radio and infrared observations, expanding the understanding of the star's surroundings. You consider the role of long-term monitoring. Magnetars are dynamic, with rotational slowdown, field decay, and bursts occurring over timescales from milliseconds to decades. Continuous observation captures these changes, producing light curves and pulse timing data. You notice that even subtle trends in spin-down rate, spectral hardness, or emission intensity reveal information about the evolution of the star's magnetic field and interior structure. These measurements are cumulative, providing a record of activity over the star's lifetime. Burst detection involves real-time analysis. Instruments detect sudden increases in photon count, triggering automated recording of the event. You observe that these flares, which can last from milliseconds to minutes, require high time-resolution instruments to capture the rapid evolution of flux and spectrum. Observing bursts allows scientists to measure energy release, particle acceleration, and magnetospheric behavior directly. Each detection adds to the understanding of magnetar activity in extreme conditions. Radio observations complement high-energy measurements. Some magnetars emit sporadic radio pulses, often linked to X-ray activity. You notice that radio telescopes, such as the Parkes and Green Bank observatories, detect these emissions using sensitive receivers and pulse timing techniques. Radio signals provide independent verification of rotation period and sometimes reveal magnetospheric changes invisible in X-rays. By combining radio and high-energy data, scientists achieve a more complete picture of the magnetar's behavior. You notice that modeling and simulations play a key role in interpreting observations. Physical models of magnetar interiors, magnetic field decay, and particle acceleration are compared with observed pulse timing, spectra, and burst properties. You observe that discrepancies between predictions and measurements prompt refinement of models, improving understanding of extreme matter, superfluid interiors, and magnetohydrodynamic processes. Simulations allow scientists to explore conditions impossible to reproduce in a laboratory. Timing observations also reveal connections between magnetic field strength and spin-down rate. You notice that by measuring how quickly rotation slows, scientists can estimate the strength of the magnetic field using well-established physical relationships. These measurements are verified against emission properties, such as X-ray luminosity and flare frequency, providing multiple independent confirmations of the field strength. You sense that the precision of these methods is remarkable, considering the vast distances and extreme conditions involved. Data processing is essential for extracting signals from background noise. Space-based instruments record enormous quantities of raw data, including cosmic rays, solar particles, and instrumental effects. You notice that advanced algorithms filter out noise, identify real photons, and correct for detector response. Each photon that survives this processing contributes to an accurate representation of the magnetar's activity. You sense the care required to ensure that observed variations reflect the star's behavior, not instrumental or environmental artifacts. You reflect on the need for multi-wavelength coordination. Magnetars may emit across the electromagnetic spectrum, from radio to gamma rays. Coordinating observations allows scientists to capture simultaneous events, linking surface activity, magnetospheric processes, and relativistic particle acceleration. You notice that precise timing and cross-calibration are essential, as even millisecond differences can influence interpretation. By integrating observations, researchers build a comprehensive picture of the star's structure, rotation, and magnetic field dynamics. Observing magnetars also requires patience and consistency. Some stars remain quiet for decades, punctuated by rare bursts. You notice that monitoring programs must operate over years to capture full activity cycles, revealing long-term evolution. Trends in spin-down, spectral changes, and flare frequency allow scientists to understand how the star's magnetic field decays and how interior dynamics evolve over time. Even periods of apparent inactivity contribute valuable information to the long-term dataset. Through these methods, you see how astronomers confirm properties of magnetars. Rotation is determined through pulse timing, magnetic field strength through spin-down and emission modeling, and surface activity through spectra and light curves. Observations provide indirect access to the interior structure and extreme physical conditions. You notice that despite being invisible to the eye, these stars can be studied with remarkable precision, revealing the fundamental physics governing matter, magnetism, and radiation. You consider the broader significance of these observations. Each detection, each measurement, allows scientists to test theories of dense matter, magnetic field decay, and relativistic effects. You observe that magnetars act as natural laboratories, where conditions unattainable on Earth can be inferred and studied. Observational astronomy becomes a tool for probing fundamental physical laws in the most extreme environments in the galaxy. You begin by scanning the Milky Way for the compact, high-energy objects classified as magnetars. Unlike typical stars, they are few in number, each discovered through bursts of X-rays or gamma rays. You notice that their rarity reflects both their brief lifetimes in astronomical terms and the specific conditions required for their formation. Only the most massive progenitor stars, ending their lives in powerful supernovae, produce the ultradense neutron stars capable of developing the extreme magnetic fields of a magnetar. Mapping their positions, you see that magnetars are concentrated primarily in the galactic plane, where massive stars are born and evolve. You observe clusters near star-forming regions, remnants of stellar nurseries where the progenitors once lived. Supernova remnants often surround magnetars, providing evidence of the violent events that created them. These shells of gas and dust, expanding over thousands of years, carry information about the original explosion's energy and composition. You notice that precise measurements of location and motion allow astronomers to trace magnetars back to their birthplaces. Proper motion studies reveal how the stars move relative to the galactic plane and local clusters. You see that some magnetars receive small kicks during supernova explosions, altering their trajectory. These motions are generally modest, keeping magnetars within regions of high stellar density, reinforcing the link between massive stars and their compact remnants. Population statistics indicate that magnetars are extremely rare. You calculate that for every few hundred ordinary neutron stars, only one or two may reach the magnetic intensity necessary to be classified as a magnetar. This rarity is consistent with models of stellar evolution, where specific mass ranges and rotational histories determine the amplification of magnetic fields. You notice that observational selection effects, including distance and emission patterns, further limit the number that can be detected, but careful monitoring gradually increases the catalog of known objects. You explore the associations between magnetars and supernova remnants in detail. Each remnant provides a timestamp and energy record for the progenitor explosion. You notice differences in remnant structure, depending on the mass, rotation, and environment of the original star. By comparing the remnant size, expansion rate, and composition, astronomers estimate the age of the magnetar and its rotational history. The remnant also contains clues to how magnetic fields may have been amplified during core collapse. You observe the distances involved. Most known magnetars are thousands to tens of thousands of light-years from Earth. You notice that even at these distances, their high-energy emissions are detectable due to the intensity of X-rays and gamma rays. Observing from orbit, satellites can capture both persistent emissions and bursts, revealing the star's rotation, magnetic field, and surface activity. You understand that despite vast separations, precise measurement techniques allow detailed study of these extraordinary objects. The age distribution of magnetars is another important aspect. Younger stars, often less than 10,000 years old, display more frequent flaring activity, higher rotational rates, and stronger magnetic fields. Older magnetars, with fields slowly decaying, tend to be quieter and spin more slowly. You notice that this progression provides a timeline for magnetic evolution, linking observed activity to both initial conditions and long-term field decay. By comparing multiple magnetars, astronomers can piece together an evolutionary sequence. You consider the variety among magnetars. While all share extremely strong magnetic fields and dense cores, some are more active than others. Certain stars exhibit repeated bursts and flares, while others emit mostly persistent radiation. You observe that differences arise from magnetic configuration, rotation, and local environment. Even subtle variations in crustal structure or field topology can significantly affect activity patterns, revealing the sensitivity of these extreme objects to initial conditions. You notice that magnetars are rarely found outside the galactic plane or in globular clusters. Their progenitor stars are massive, short-lived, and formed in dense stellar regions. As a result, magnetars generally remain close to their birth sites, offering insight into galactic structure and star formation patterns. You observe that tracking their distribution helps scientists study stellar populations and the frequency of massive supernovae, connecting individual magnetars to broader galactic processes. Some magnetars have been linked to transient radio emission, a rare phenomenon. You notice that the combination of high-energy radiation and occasional radio bursts provides multiple windows into magnetar behavior. These observations reveal correlations between surface activity, magnetic field decay, and particle acceleration. By studying these patterns, astronomers refine models of magnetic field evolution and the mechanisms behind flaring events. You consider the relationship between rotation and observed properties. Younger, faster-spinning magnetars often produce more energetic bursts, while slower rotators tend to be quieter. You observe that rotational energy, while secondary to magnetic energy in most cases, influences the timing and intensity of emissions. Tracking spin-down rates across the population provides both age estimates and insight into long-term magnetic decay. The magnetic field strength of magnetars is exceptional. You notice that measurements, derived from rotational slowdown, flare intensity, and spectral analysis, indicate surface fields exceeding 10 superscript 1 to 10 superscript 1 Gauss. These fields are thousands of times stronger than typical neutron stars, and trillions of times stronger than Earth's magnetic field. You understand that such intensity affects the crust, magnetosphere, and surrounding space, producing both observable radiation and structural stresses that define magnetar behavior. Population studies also reveal trends in flare frequency and intensity. Younger, stronger field magnetars flare more often, while older ones produce rare or minor events. You see that monitoring multiple stars over years allows astronomers to establish statistical relationships between age, magnetic strength, and activity. These correlations improve predictive models and inform understanding of magnetar formation, evolution, and eventual transition to quieter neutron stars. You reflect on the broader implications of these observations. By mapping magnetars, associating them with remnants, and measuring their properties, scientists connect individual objects to the life cycle of massive stars. You notice that these stars are both extreme and informative, providing a link between supernova physics, magnetic field generation, and the distribution of stellar remnants in the galaxy. Understanding magnetars illuminates not only their individual behavior but also the broader processes shaping the Milky Way. You turn your attention to the most extreme events produced by magnetars, giant flares. These bursts of energy are orders of magnitude more powerful than typical stellar flares, releasing immense amounts of radiation in seconds. You notice that giant flares are rare but dramatic, providing a clear signal detectable across the galaxy and, in exceptional cases, even in nearby galaxies. Their energy output rivals the total energy the Sun emits over tens of thousands of years, condensed into a brief, intense flash. The source of a giant flare lies in the magnetar's magnetic field. You observe that as the field evolves and twists, stress builds within the star's crust and magnetosphere. When this stress surpasses a critical threshold, it is suddenly released, producing a catastrophic rearrangement of magnetic field lines. This magnetic reconnection accelerates particles to relativistic speeds, producing gamma rays, X-rays, and high-energy electrons. You notice that the combination of crustal fractures and magnetic reconnection defines the intensity and duration of the flare. Giant flares typically begin with a brief, intense spike of gamma rays. You observe this initial spike lasting less than a second, with photon energies reaching hundreds of keV to several MeV. The flare then transitions to a longer, gradually declining tail, modulated by the star's rotation. You notice that periodic pulses in the tail correspond to the Magnetars spin period, offering a precise clock to study both rotation and magnetic geometry. Each detected flare carries information about the star's internal and external magnetic configuration. High-energy photons from the flare propagate through space, traveling thousands to millions of light-years without significant absorption. You notice that these photons allow astronomers to detect flares far beyond the Milky Way, providing observational data on both the flare itself and the intervening interstellar medium. The arrival times, energy distribution, and pulse modulation all encode information about the magnetar and the environment through which the radiation has passed. The energy released in a giant flare is immense. You calculate that even a single event can release 10 to 10 ergs of energy, equivalent to the total energy emitted by the sun over tens of thousands of years. You notice that such energy is sufficient to heat surrounding plasma, drive shock waves through the magnetosphere, and accelerate particles to extreme velocities. The flare's impact on nearby matter can extend far beyond the immediate vicinity of the star, influencing radiation, particle populations, and the local magnetic environment. Giant flares provide direct evidence of magnetic decay. You observe that the release of energy corresponds to a decrease in magnetic field stress, demonstrating that the field is not static but evolves over time. By comparing multiple flares from the same magnetar, scientists estimate decay rates, field topology changes, and the timescale over which energy is stored and released. This insight into magnetic evolution is crucial for understanding both the life cycle of magnetars and the physics of ultra-strong magnetic fields. You notice that flares interact with the magnetosphere in complex ways. Particles trapped along field lines are suddenly accelerated, producing synchrotron radiation and secondary high-energy photons. The rearrangement of field lines can induce currents, redistribute charged particles, and alter emission patterns. By studying flare light curves and spectra, astronomers reconstruct the dynamic behavior of the magnetosphere during these extreme events. Each flare becomes a natural experiment in the physics of magnetic reconnection and particle acceleration. The tail of a giant flare reveals rotational properties. You see that pulses correspond to hotspots aligned with the magnetic poles. The brightness of each pulse varies as the star spins, producing a characteristic modulation. You notice that these pulses allow precise measurement of rotation period, rotational slowdown, and changes due to glitches. Even the decay rate of flare brightness carries information about magnetic field strength and energy dissipation. Observations of giant flares also help identify magnetars in distant regions. You notice that flares are far brighter than typical X-ray emissions, making them detectable at large distances. Even when other indicators are weak or absent, a single flare can confirm the presence of a magnetar. Detection across multiple instruments allows cross-validation, confirming the source, distance, and energy output. These events provide both discovery and diagnostic power in astrophysical research. Giant flares produce high-energy particle outflows. You observe that relativistic electrons and ions are ejected along magnetic field lines, contributing to observable synchrotron emission and, in some cases, interactions with interstellar material. These outflows carry energy and momentum, subtly affecting the local galactic environment. Even at distances of tens of thousands of light-years, secondary effects can be measured, demonstrating the far-reaching influence of a single magnetar flare. The timing of flares provides insight into stress accumulation. You notice that most flares occur in younger, highly magnetized stars, consistent with models predicting that stronger fields accumulate stress faster. Older magnetars with decayed fields produce smaller, less frequent events. You observe that flare frequency and intensity correlate with rotational period, magnetic geometry, and crustal composition, offering a statistical framework for understanding energy release in extreme magnetic environments. You consider the broader astrophysical implications. Giant flares release energy comparable to some short gamma-ray bursts observed in distant galaxies. You notice that studying magnetar flares helps distinguish between different sources of high-energy transients, informing models of stellar evolution, magnetic decay, and cosmic particle acceleration. By comparing flare properties with galactic environment and progenitor characteristics, scientists build a more complete understanding of how massive stars leave behind compact, high-energy remnants. Detection methods rely on rapid, precise instrumentation. You observe that satellites and observatories monitor the sky continuously, capturing sudden increases in photon counts. Real-time data processing allows identification of flares within milliseconds, triggering follow-up measurements across multiple wavelengths. You notice that even a brief delay can affect the ability to characterize the flare's initial spike, emphasizing the importance of coordinated observation and high time resolution. You notice that giant flares also inform models of neutron star interiors. The energy released, the timescale of pulses, and the spectral distribution of radiation reveal how stress is stored in the crust and how magnetic reconnection occurs in the magnetosphere. Each flare provides constraints on equations of state, superfluid behavior, and nuclear interactions at extreme densities. Observational data, combined with theoretical models, allow scientists to probe physical conditions inaccessible on Earth. Finally, you observe that these cosmic signals carry more than raw energy. They encode the structure of the magnetosphere, the rotation of the star, and the dynamics of magnetic decay. By carefully analyzing light curves, spectral evolution, and pulse modulation, astronomers decode the underlying physics governing the flare. You notice that these events, though brief, serve as profound lessons in extreme matter, high-energy astrophysics, and the interaction between magnetism and relativistic environments. You turn your attention to the long-term evolution of magnetars, beyond what can be directly observed. While bursts, flares, and pulses provide snapshots, theoretical models help you understand their gradual changes over thousands to millions of years. The magnetic field, though extraordinarily strong, is not static. You notice that it slowly decays, releasing energy that heats the crust and powers persistent X-ray emission. The decay follows predictable physical laws, influenced by the field's configuration, the star's conductivity, and internal dynamics. The decay of the magnetic field occurs through multiple mechanisms. You observe that ohmic dissipation converts magnetic energy into heat, while Hall drift redistributes the field within the crust. Over time, these processes reduce the overall intensity of the field and change its geometry. You notice that field decay is faster in younger, more strongly magnetized stars, producing high-energy activity initially, followed by a gradual quieting as the field weakens. Understanding these mechanisms allows scientists to model magnetar lifespans and predict future behavior. Cooling of the neutron star is another important aspect. You notice that freshly formed magnetars are hot, with surface temperatures of millions of degrees. Neutrino emission dominates the cooling in the first thousands of years, carrying energy away from the core. As the star ages, photon emission from the surface becomes the primary cooling mechanism. You observe that the interplay between magnetic heating and radiative cooling determines the persistent X-ray luminosity, which gradually diminishes over time. Rotation evolves alongside magnetic decay. You see that the initial spin period is often very short, a few seconds or less, but magnetic braking slows the star over thousands of years. The torque applied by the magnetized wind reduces angular velocity, and the spin-down rate provides insight into both the field strength and its evolution. You notice that by combining spin measurements with X-ray observations, scientists can estimate the age and energy budget of the star with remarkable accuracy. You consider the eventual transition to a quieter neutron star. As magnetic stress decreases, bursts and flares become rare or disappear entirely. The star remains dense, spinning slowly, and cooling over millions of years. Its field may resemble that of ordinary pulsars, weaker and more stable. You notice that even in this quiet phase, the magnetar retains its extreme density and compact structure, but its high-energy activity has largely faded, marking the end of the most dramatic evolutionary stage. Crustal properties influence long-term behavior. You observe that the rigidity and composition of the crust affect how stress is stored and released. Fractures become less frequent as the field decays, and thermal evolution influences the conductivity of crustal layers. These factors together shape the observable activity, creating patterns that can be compared across multiple stars to test theoretical models. You notice that understanding crustal physics is essential to predicting flare frequency, rotational glitches, and long-term luminosity trends. Internal processes also evolve. Superfluidity in the core plays a role in angular momentum redistribution and glitch events. You notice that superfluid vortices interact with the crust, affecting rotational behavior over long timescales. Magnetic flux tubes can migrate or rearrange, subtly altering internal field configurations. You see that the interplay between core and crust produces measurable effects, even when the star is no longer producing dramatic flares. Long-term monitoring of spin and luminosity reveals these slow, underlying dynamics. Magnetospheric changes accompany internal evolution. You notice that as the magnetic field decays, the structure of the magnetosphere adjusts. Twisted field lines relax, reducing particle acceleration and high-energy emission. The density and composition of the magnetospheric plasma also change over time. By modeling these adjustments, scientists can predict how persistent X-ray luminosity evolves and how the magnetosphere responds to the decreasing magnetic stress. Theoretical models also address the rarity of magnetars. You observe that only a small fraction of neutron stars develop magnetic fields strong enough to produce the observable phenomena. Factors include progenitor mass, rotation rate at birth, and initial field configuration. By modeling stellar evolution and supernova dynamics, scientists can reproduce the observed population statistics, connecting the formation of magnetars to the broader life cycle of massive stars. You notice that this approach integrates both observational and theoretical insights. Field geometry evolves alongside intensity. You notice that initially complex, twisted configurations gradually simplify as currents dissipate. This evolution affects not only high-energy emission but also pulse profiles observed from Earth. As the field relaxes, periodic modulations become smoother, bursts become less frequent, and the magnetar approaches a state resembling ordinary neutron stars. Understanding this process allows scientists to relate early activity to eventual quietude, tracing the full life cycle of the star. Cooling curves also provide insight. You see that as the star radiates heat through X-rays and neutrinos, its surface temperature declines steadily. Observations of older magnetars show cooler surfaces, consistent with models of field decay and thermal evolution. Temperature measurements combined with magnetic and rotational data allow scientists to reconstruct the energy history, estimating both the initial magnetic intensity and the timing of major events. You notice that this long-term perspective reveals the interplay between energy storage, release, and dissipation over millennia. You notice that giant flares become increasingly rare as the magnetar ages. Early in life, stress accumulates rapidly, producing frequent bursts. Over tens of thousands of years, the rate of energy release declines, and flares become sporadic or absent. This reduction corresponds with the decay of the magnetic field and changes in crustal stress distribution. You see that even in quiet stars, minor glitches or small bursts may occur, leaving subtle signatures in rotational timing or persistent emission. You reflect on the importance of modeling combined effects. Cooling, magnetic decay, rotation, and crustal physics all interact to produce the observable properties of aging magnetars. You notice that long-term models predict the fading of high-energy activity and the eventual emergence of a more stable neutron star. By comparing predictions with observations across multiple stars, scientists refine these models, testing assumptions about conductivity, superfluidity, and field evolution. Each magnetar contributes data to this broader understanding. You consider the ultimate fate of a magnetar. After millions of years, the star's magnetic field weakens, crustal activity ceases, and rotation slows to low rates. The star becomes nearly invisible in high-energy bands, a cold, dense remnant quietly tracing its orbit around the galaxy. You notice that its structure remains extreme, a sphere of neutrons packed to extraordinary density, but its energy output has diminished. In this phase, the magnetar joins the broader population of old neutron stars, a relic of massive stellar evolution. You rest your attention on the totality of what a magnetar represents. Dense, spinning, and immensely magnetic, it embodies physical extremes that push the limits of known science. You notice that every measurement, every observation, reveals fundamental principles at work. Density, magnetic fields, relativistic effects, and energy release all coexist in a natural laboratory where physics operates at conditions impossible to replicate on Earth. By observing these stars, you gain insight into the behaviors of matter, radiation, and spacetime under extreme conditions. The density of a magnetar's interior is staggering. You imagine a mass greater than the Sun compressed into a sphere barely tens of kilometers across. Neutrons dominate the core, and the gravitational forces prevent further collapse. You notice that this density affects every aspect of the star's behavior, from rotational inertia to the propagation of seismic waves through the crust. You sense that studying these dense objects allows scientists to test equations of state for matter under extraordinary pressure, exploring physics inaccessible in terrestrial laboratories. Magnetic fields define the environment surrounding the magnetar. You observe that field strengths reach up to 1,000 trillion times the Earth's magnetic field, confining charged particles and shaping the magnetosphere. These fields store vast amounts of energy, capable of producing bursts and flares detectable across the galaxy. You notice that the study of these magnetic extremes informs our understanding of fundamental electrodynamics, particle acceleration, and the interaction of radiation with matter in ultra-strong fields. Rotation provides another dimension of measurement. You see that pulse timing and spin-down rates offer precise clocks, revealing both the star's current energy state and its evolutionary history. Small variations in rotation provide insight into internal processes, including superfluid motion and crustal dynamics. By observing these minute changes, scientists gain an understanding of the complex interplay between rotation, magnetic fields, and stellar structure. The extreme environment of a magnetar affects nearby matter and light. You notice that particles in the magnetosphere follow magnetic field lines, accelerated to near-light speeds, while photons climbing out of the gravitational well experience redshift. Observations of radiation allow measurement of both the star's magnetic strength and the curvature of surrounding spacetime. Each photon carries encoded information about density, energy, and field configuration, a continuous message from the extreme physics near the surface. High-energy events demonstrate the power stored within magnetars. Giant flares, bursts, and glitches release enormous energy in fractions of a second. You see that these events reveal the dynamics of magnetic stress, crustal fracture, and energy release. Studying these phenomena provides insight into magnetic reconnection, particle acceleration, and the limits of stellar material. Each flare, though brief, carries lessons about energy transfer, force interactions, and the behavior of matter under conditions beyond everyday experience. You consider the observational techniques required to study these stars. X-ray and gamma-ray satellites capture photons invisible to the eye, while pulse timing, spectral analysis, and multi-wavelength observations decode the structure and activity of magnetars. You notice that each technique complements the others, providing independent verification of magnetic strength, rotation, and energetic events. These observations demand precision and patience, reinforcing the careful, methodical approach necessary to explore extreme environments. The rarity of magnetars emphasizes the specificity of conditions needed for their creation. You observe that only the most massive progenitors, with rapid rotation and particular magnetic configurations, produce the stars capable of such phenomena. Their scarcity makes each detection significant, a unique opportunity to study extreme physics. By examining population statistics, spatial distribution, and associations with supernova remnants, scientists trace the connection between massive stars, supernova mechanics, and the magnetic intensity observed in these remnants. You notice that theoretical models provide context for observations. Field decay, cooling, and rotational slowdown explain both short-term behavior and long-term evolution. Simulations of magnetic reconnection, crustal stress, and magnetosphere dynamics allow predictions that can be compared with real data. You see that theory and observation together form a continuous dialogue, each informing the other, providing a full understanding of the physics governing these extraordinary stars. You reflect on the life cycle of a magnetar. From formation in a violent supernova to periods of extreme activity and eventual quieting as fields decay and rotation slows, the star traces a path through multiple energetic regimes. Each stage offers measurable effects, from bursts and flares to persistent X-ray emission and eventual transition to an ordinary neutron star. You notice that this evolutionary path reinforces the continuity of physical laws, showing how extreme conditions emerge naturally from known processes. You consider the subtle interplay between observation and theory. Every flare, pulse, and emission profile contributes data that refine understanding. Each measurement, from spectral energy distribution to rotational period, provides insight into magnetic geometry, crustal stress, and field decay. You notice that the universe allows scientists to read these imprints, translating the behavior of distant stars into concrete physical understanding. Even the faintest or most distant magnetar carries lessons about high-density matter, magnetism, and relativistic effects. Energy in magnetars is both immense and constrained. You observe that while the total energy is far beyond ordinary experience, it follows predictable physical laws. Magnetic stress accumulates, energy is released, and fields decay according to established principles. You notice that this controlled behavior, despite extreme values, demonstrates the universality of physics. Even in the most violent environments, matter and energy follow consistent rules. The extreme properties of magnetars also provide insight into the behavior of spacetime. Frame dragging, gravitational redshift, and relativistic motion of particles are all observable near these stars. You see that studying these effects confirms general relativity under extreme conditions and tests our understanding of gravity, rotation, and high-density matter. Observing magnetars thus bridges astrophysics and fundamental physics, connecting distant cosmic events to underlying principles of the universe. You notice the elegance of cumulative understanding. Density, magnetic intensity, rotation, energy release, and spacetime curvature together form a coherent picture of a highly complex object. Observations and models converge to reveal predictable patterns, despite the star's extreme nature. You see that careful study transforms what could seem chaotic into measurable, understandable phenomena, allowing insight into both the star itself and the broader physical laws it exemplifies. Even in quiet moments, magnetars teach lessons. Persistent X-ray emission, slow spin-down, and gradual field decay provide long-term data. You observe that subtle changes, recorded over decades, yield profound understanding of magnetic evolution, thermal behavior, and rotational dynamics. By following the star's evolution over time, scientists gain a comprehensive view of extreme physics in action, reinforcing principles of energy conservation, magnetic dynamics, and relativistic behavior. You reflect on the human perspective. Observing, measuring, and modeling magnetars requires patience, precision, and careful interpretation. You notice that the information carried by these stars, spanning millions of light-years, can be decoded into concrete understanding of matter, energy, and spacetime. Each observation links the extraordinary to the comprehensible, allowing the mind to trace the physics of extremes in a calm, systematic way. You sense the continuity of extreme physics across the universe. Magnetars are unique, yet they are part of a spectrum of neutron stars, connecting ordinary pulsars, supernova remnants, and compact objects. Observing them helps you understand the broader astrophysical context, linking individual stars to galactic evolution, supernova mechanisms, and the life cycle of matter. You notice that this perspective emphasizes both the uniqueness and the universality of physical laws.